And then 1.3, this is quite an interesting one. Two blocks P and Q of masses M1 and M2 respectively are held at rest on a frictionless horizontal floor with a compressed spring between them as shown below. And then when the blocks are released and the spring drops to the floor, block Q moves to the right with a velocity v. Right, which one of the following represents the momentum of block P after the blocks are released? Right, so I want you to think about something. I want you to think about the conservation of linear momentum, right? Before the spring was released, the total momentum was 0, right? So after it is released, the total momentum should also be 0, right? So after it was released, the momentum of Q, right? The momentum of Q will be equals to M2 multiplied by V. That's what we have, right? And then what about the momentum of P? What about the momentum of P? Right? A few people would think that, oh, okay, the velocity of P should be half the velocity of Q because P is 2 times Q. But then it looks like P is bigger than Q. But then you're not told. You cannot just conclude that P is larger than Q, right? I mean, what if the density is different and actually Q is weighs more than P, right? Such things can happen. So you cannot conclude that P is greater than Q or Q is less than P and so on by just looking at them. Because what about density? If the momentum of Q is 3 units to the left, then we would expect the momentum of P to be 3 units to the right. Because when we add those two, we're going to get a total momentum of 0, which is what we're looking for, right? I'm saying that to say that if the momentum of Q is M2 multiplied by V to the right, then the momentum of P is also M2 multiplied by V. But this time, to the left, right? The momentum need to be the same magnitude, but in opposite directions, so that the linear momentum is conserved. And that is option D. So the answer to 1.3, we have D.